All right, so today's video is going to focus on experimental design. So an experiment is when you are imposing a treatment or treatments on subjects, and you are trying to see if there are differences in those treatments. We have explanatory variables, and those are sometimes also called factors. And that is a part of what is involved in assigning treatments. So, like, here's an example where maybe I'm measuring response time and I'm going to have subjects look at a computer screen, and on the computer screen, there's going to flash something. And that something might have a different color and it might have a different shape. So color and shape would be my factors, which are also called explanatory variables. And I might have different levels of each of those. So one of my explanatory variables is color, but I could have 3 different levels: red, yellow, green. Another explanatory variable would be shape, and I can have 2 different levels of that: circle and square. So these are things that I'm using and assigning to my subjects, my experimental units. Subjects we usually refer to for humans, but experimental units could be dogs, could be trees, could be fish, could be an entire tank of fish. It could be a petri dish of things in the dish. Ooh, how do we spell petri? Ooh, I might have totally spelled that wrong. Don't laugh at me. So these are some kind of terms you're going to see when you are conducting experiments. But the idea is we want to impose a treatment on a subject or experimental unit to reveal the response of one variable to changes in the explanatory variable, which are also known as factors. A response variable, I think I might have that. Yep, on this page. So a response variable is like the result or the thing that you are measuring. So in my example before with the shapes and the colors, I said I was going to measure response time or reaction time. So that would be the response variable. The treatments, I kind of already mentioned that, but the treatments would be the different combinations. So I could have red circle, red square, yellow circle, yellow square, green circle, green square. So the different combinations of levels and factors make up your treatments. Control group. We want to control the effects of lurking variables. We want to keep all the other factors constant except the treatments so that we can just compare the treatments. So a control group could be a group that gets 0 medication, let's say. But I could give them a placebo, which would be a pill that looks and tastes like the other pills, but has no effect. So that would be like a pill with 0 milligrams of the actual medicine. Now, a control group could be that. It could be 0 milligrams. Or a control group could be an already established treatment. Let's see. I don't know how else I want to phrase that. Let me think for a minute. Okay, so for example, let's say I was gonna do a new medication. Let's say I'm doing a new medication for pain relief, just general pain relief. Okay, now I could compare my new medication against a placebo, but I mean, I probably will see results. Like, I'll probably see some positive results. Like, any medication will probably be better than no medication, right? So, like, I'm gonna see positive results, but duh, you know? Um, so maybe my control group could be like Tylenol. Like, I'm gonna do a new pain relief medication against an already established one, a well known one, like Tylenol. Because then that way I can see if mine works better than Tylenol does. So sometimes comparing something against nothing doesn't really give you interesting results. Um, Here's the big three of experimental design: control, randomization, and replication. Um, Try to control everything you possibly can, whether that's a control group or you're just controlling for, like when we talked about like taste testing Coke versus Pepsi, you would want to have the same temperature. You would want to have the same amount. You would want to have the same freshness. You would want to serve it in the same cup, etc. So all of those things we want to control for so that those don't become issues later. You know, like if we have different temperatures, if Coke is cold and Pepsi is room temperature, people might say they like Coke better just because it's cold. And we want to eliminate that lurking variable. Randomization. There has to be randomization. So either we, um, well, I mean, we would love for our subjects to be chosen randomly, but sometimes they're not. Sometimes they're volunteers. So then, where randomization can come into play is we assign our subjects to treatments randomly. Okay, so we are not the ones who decide who goes where. It should be like a flip of a coin, or it should be drawing names out of a hat, or something like that. And your experiment should always be able to be replicated. We want to perform this experiment as many times as possible to get a lot of data. All right, single blind versus double blind. Um, Single blind is when the subject doesn't know what treatment group they're in. Double blind is when the subject doesn't know, but also the people interacting with the subject doesn't know. So maybe it's a nurse that is handing out medication. That nurse might not know what medication the person is receiving. They just have, a container with that patient's name on it that they open up and give to the patient. Someone does know. The actual researcher knows, they're the ones behind the scene. They know what's happening, but the subjects and the people interacting with the subjects, they don't know. We don't want these people to give away anything or to interact in such a way that could cause bias. So we just want to eliminate that. So double blind is the way to go if you can, but it's not always feasible. Block design. This sometimes gives people a little bit of trouble. If you think that something might affect your results, so maybe we think gender affects results in some way. Maybe we think men and women are going to respond differently. Then I would block by gender. So I would have men in one group, I would have women in a separate group. Now, within this group, we assign our treatments randomly. So maybe these men are let's pretend there's 30 men, and we're going to randomly assign 10 men into group 1 who's going to receive treatment 1. 10 men will go into group 2, they receive treatment 2. 10 men will go into group 3 receiving treatment 3. And then I compare the results just among the men. And then I can kind of say like what treatment might be best for men. And then let's say maybe I have 60 women These groups might not be equal. But let's say I have 60 women and I assign 20 of them to take treatment 1, 20 of them take treatment 2, and 20 of them take treatment 3. And then I'm going to compare the results just among the women. And then maybe I'll be able to say a specific treatment helps women, and then a different treatment maybe helps men. It's essentially like a mini experiment within a larger experiment. So an experiment among the men, an experiment among the women within a larger experiment. So here I would have 90 total subjects. Now you do not form these groups randomly. You don't like go up to a person, flip a coin, and say you're going to be in the men group and you're going to be in the woman group. These are not formed at random. The randomization comes in with the treatments. And again, you block based on something that you think is going to cause a different response. All right, so here's some things more about blocking. So I already mentioned this. We don't randomly assign subjects into blocks. Rather, we divide our subjects up in advance. You don't just block for the heck of it. You block based on some factor that you think will impact the response to the treatments. Whoops. Then we randomly assign treatments within each block, creating 2 or more miniature experiments. Blocks should be similar within, but very different between. So similar within, similar meaning all of these are men, similar within, all of these are women, but different between. And then you can only make comparisons within the block, not between the blocks. So I can only make comparisons within the men, I can only make comparisons within the women, but I do not compare between men and women. And sometimes up here, people get blocking confused with stratifying because it's very similar. But stratifying is when you are choosing a sample of people. So that would happen, if you were going to do that, that would happen before the experiment even starts. That's how you get the people to be in your experiment. And then blocking is the experiment itself. Now, you don't have to do both of these together. You can, but it doesn't have to work that way. Let's see, anything else? Oh, matched pairs. So we've talked about this a bunch, but just remember you can do it a couple different ways. You can pair 2 people up. So these 2 people are similar, and I would flip a coin and randomly assign, let's say heads, you get treatment 1, tails, you get treatment 2. So let's say I take this person and I flip the coin and it's tails. This person will get treatment 2, so this person will get treatment 1. And then we're going to compare. Or it can be one person and that person receives both treatments. And the order that they receive those treatments is randomly assigned. And we have to do that randomly because what if treatment 1 somehow affects treatment 2, or vice versa? So we want to randomly assign those treatments to avoid any of that. And nothing else from that page. Okay, lurking variables versus confounding. I've kind of already mentioned lurking variables. So that would be some variable not among the explanatory or the response. It would be a third variable. And it will influence the relationship. Sometimes we don't even know it's there, but that's why we want to control. So a lurking variable would be like temperature of the Coke and Pepsi. If I don't control that temperature, then temperature might become a lurking variable that might affect my responses. confounding kind of goes along with this. I like to think of it as like confusing. So I don't know if okay, let me give an example. I think I've done this one a lot. Laundry. Um, and let's say I am trying to figure out detergent, and maybe I do detergent A with this load and I wash it in cold water, and I do detergent A, or I'm sorry, detergent B with this load and I do it in hot water. Okay, so there's going to be confounding involved here because I don't know if my results are going to be due to the detergent or due to the temperature, because temperature also affects how your laundry cleans. So that would be like temperature would be confounded with detergent type. So I should have controlled the temperature here. Temperature was kind of a lurking variable. I should have controlled for that and had the same temperature so that the only difference was the detergent. Okay, that is it for experimental design for today. And then eventually here we're going to be moving into probability stuff, all things probability. Okay, have a good day.